Okay, good morning to one and all. So welcome to VLSI class. Today, in the last class, we discussed about the scaling parameters with the mass structures, okay, mass circuits. Now, let's go to constant level. Once again, we'll continue the same topic. So in the last, let's consider this switching energy per gate, okay. So already we know that switching energy per gate, basically energy is nothing but we're having the half CV square formula. So by using that half CV square, we consider that here EG energy per gate is switching energy per gate is nothing but EG, that is gate energy you can say, that is equals to half CV square. That means half C means CG, and V means VDD whole square. Okay, half of CV square. So in this case, half is not a constant value, so no need to scale down this value. This is always equal to 1. And we know the value of CG. Okay, what is CG? Yes, CG is equals to gate capacitance. So it is equals to beta by alpha square. Okay, and VD is scaled down by beta square, 1 by beta. Okay, so it is nothing but 1 by beta square. So that is equals to 1 by alpha square into beta. So like this, you can switching energy per gate can be scaled down. Similarly, the power dissipation per gate. Power dissipation per gate. And basically power dissipation, that is the power comprised, that is the power dissipation consists of two components. One is called static component and that is called a dynamic component. So PG is equal to PGS plus PGD. This is the static power dissipation and this is the dynamic power dissipation of the gate. And the static power dissipation, basically what happens is the current which is flow from VDD line to VDD to ground rail when the transistor will be turns on. Okay, so therefore we can consider some amount of the static current is given by VDD by or on of the transistors, total resistance between VDD and VS, VG ground. So therefore R on we have to consider here. So VDD whole square divided by R on. This is called static current. Similarly, dynamic power dissipation depends upon the frequency. So therefore, dynamic power dissipation is equal to EG. There is the nothing but switching energy per gate multiplied by the frequency of naught. Okay. So both the factors here scaled down by beta square here. EG is equal to already we scale 1 by alpha square into beta. Similarly, F naught is equal to, so F naught is equal to alpha square by beta. So therefore, this value is equals to, so 1 by alpha square into beta and also alpha square by beta. That is alpha square cancels to get 1 by beta square. Okay, so the PG total dynamic power is equal to 1 by beta. So good by beta square. Okay, so therefore substituting these values in this case, so the total value are scaled down by 1 by beta square. Okay, so there is 1 by alpha square into beta square into beta by alpha square divided by this value. So that is alpha cancels. So you'll get to 1 by beta and 1 by beta is equal to 1 by beta square. Okay, so that is about power dissipation per gate. Okay, static and dynamic components. Similarly, power dissipation per unit area. This is also important. This is the power dissipation per gate and this is the power dissipation per unit area. Right. So that is equals to PG by BA power dissipation per unit area, PA is equal to PG by some value. 1 minute. So power dissipation per unit area. So it is nothing but power dissipation is equal to PG per area, AG. Okay, power dissipation per unit area is nothing but PA we can call. So there is a power dissipation PG per area, AG. So therefore, power dissipation is equal to 1 by beta square divided by A. Okay. So that is 1 by beta square divided by 1 by alpha square. That is equals to alpha square into beta square. Right? Alpha square into beta square. So that like this, you can scale down the power dissipation per area. Okay, this is the power dissipation per area. Okay, and similarly, we are having the last one is called power speed product. It is the product of power and the speed. Delay, power and speed. That means power means you can consider the total power. The power dissipation is equal to power dissipation per gate multiplied by the delay. Okay, the speed product depends upon the delay. So therefore, power dissipation per product, the power speed product is equals to PG into TD. You know PG here and delay. Okay, so delay is equals to beta by alpha square, right? Beta by alpha square, and PG is equal to 1 by beta square. That is equals to 1 by alpha square into beta. 1 by alpha square into beta. So this is like this, you can scale down the values in terms of alpha and beta in case of combined voltage and scaling models. Okay, so this is about the combined voltage and scaling models. Those parameters will be scaled down by this method. Similarly, let us go for the summary of the scaling effects. So let us consider we are having, so already we discussed now here, that is the combined voltage and scaling method. So we are having total 16, 15, 14, that is total 14 parameters. So once again, we can draw all these parameters here: supply voltage, channel length, channel width, oxide thickness, gate area. Okay, scaling effect. That means these are the products: gate capacitance, the gate parasitic capacitance, charge density, channel resistance, saturation current, conductor cross section. Okay, like this, all these values we are having now in this case. Okay, we can write once again: current density. Okay, logic level, logic 1 level. Okay, logic 1 level, how to represent VDD. So that is VDD can be represented by beta in case of voltage and scaling model. Okay, and the switching energy, switching dissipation per gate, gate per unit area. Okay, and now this is a gate per unit area, and also okay, gate per unit area. Remember, okay, and power dissipation per unit area. Okay, unit area is same thing in this case. Similarly, gate delay. Okay, beta by alpha square, maximum operating frequency alpha square by beta, right? And power speed product. All these values are going to represent here in this case. Okay, these are the values in terms of this combined voltage and dimension model. Okay, the combined voltage and the dimension model. All these values will be represented given here. Similarly, we are having another is constant E model and constant V model. We are having two types. Okay, so in constant E model, wherever we are having beta, replace beta by alpha. Okay, wherever replace beta by alpha. Just already given in the first class, starting of this method circle here. Just remember here. So constant field model, replace beta is equal to alpha, and constant voltage model, replace beta is equal to 1. Okay, you remember these values. So already we are having combined voltage and the dimension model. In this case, both we are using both alpha and beta. Okay, but in case of constant field model, we are using only alpha and we are using only alpha, no beta is there in case of constant field model. And in constant voltage model, we are not using, we are using only alpha here also. Okay, just replacing, we're not going to use the beta in this case. So that means, so in case of constant field model, you can replace wherever you're having beta, replace it by alpha. And wherever you're, in case of constant voltage model, wherever you're having beta, we can replace it by 1 respectively. Okay, so therefore, we can represent now in this case here. These are the combined voltage and dimension scaling model. Now, in case of constant E model, let us take VDD, supply voltage. So this supply voltage in constant E model can be held down by 1 by alpha, because this replace beta is equal to alpha. Wherever you are in this region, in this case, okay, in this table, wherever you are having beta, only beta. So replace it by alpha. Okay, there is 1 by alpha, 1 by alpha, 1 by alpha, 1 by alpha. Now it is 1 by alpha square and beta is alpha. In this case, it is alpha by alpha square is equals to alpha 1 by alpha. And this is 1 by alpha cubed as it is, right? And this is a constant term is always a constant term in case of voltage scale and E scale. So 1, 1. And this is beta is equal to alpha. And 1 by alpha square is as it is. And in this case, beta is equal to 1. It is alpha. Beta is equal to alpha. That is alpha square by alpha becomes alpha. And in this case, 1 by alpha. Again, 1 by alpha cube. Okay, alpha square into alpha. And 1 by alpha square. Alpha square. Alpha square by alpha square is equals to 1. Now, in this case, there is a gate delay is equals to 1 by alpha. And alpha square by alpha, again alpha, maximum operating frequency, and product, speed product, the power speed product is equal to 1 by alpha into beta. So it is equal to 1 by alpha cube. Similarly, in case of constant V model, okay, so we are going to use, once again, in case of constant V model, we are using, here also we are using only 1, but we are not going to use the combined V and VD model. So already we know the combined V and VD model. So here the substituting beta is equal to 1. Okay, so 1 by 1 is equal to 1. Okay, supply voltage can be replaced by 1. 1 by alpha cubed as it is here. Offset this is 1 by beta in case of combined V and D model. In case constant V model, 1 by 1 is the same, remaining will be same. In this case, 1 by alpha square, 1 by alpha square, 1 by alpha, here 1, 1, and this 1 by 1 is 1, right? And 1 by alpha square as it is. Now, in this case, alpha square by beta is equal to 1, alpha square, 1, and 1 by alpha square into beta, 1 by alpha, like this. Wherever you are having beta, replace it by 1. Okay, you will get a constant to voltage scaling model. Okay, these are the parameters you have to remember here. So remember here, now this is the constant this scaling model and the circuit. Now let's go to this is and remember from the examination point of view. So number of times they are giving some parameters. For example, in the examination they are given only current density and speed product. Okay, only these values will be they will give. So you have to remember the formula. Okay, what is the formula for current density? It is IDS by A. So because the current is not given, the IDSS is not given, but you have to write the value of the IDSS, and you have to first you can substitute the value of IDSS there. Okay, so IDSS will be failed down by 1 by beta, and then you can substitute here J is equal to 1 by beta divided by 1 by alpha square. Okay, so therefore it becomes alpha square by beta like this. Sometimes in the switching energy, for example, the examination they will give power dissipation per gate. So power dissipation per gate is equals to, you have two components. So this is VDD by Rn. So first you have to calculate the value of Rn Okay, because the RN is different, is not given in the problem circuit in the examination, but you have to write the value of R1, R0 also. You know what is the R0, RN? Okay, that is charge resistance. So this, you remember this formula and substitute here, you get this equal to 1. And don't substitute directly R0 is equal to 1, Rn is equal to 1. Okay. So in the examination, definitely you have to start from Rn value, you have to substitute the charge resistance value. Use that formula directly. Don't use directly here. So use the formula and calculate the value and then substitute here. Similarly, dynamic participation. You don't substitute the values of EG and F0 directly. First EG. EG means again it is half CV square formula. Substitute the values here. CG value and then EG, BDD. CG you have to write the value. CG is equal to F0 A by D. So by using this one, you can find the value. And then F0 is equal to directly substitute the value 1 by T0. Okay, delay. So therefore you get the value. Okay. So like this, they will give some, not all the parameters, only some parameters. They give some parameters. Sometimes they will ask you for 6 marks. Sometimes they are asking for 8 marks. Depending upon the problem, they will give the marks in this case. Okay. So you're right. Sometimes they ask you to find out constant E model. Okay. For once again, because we know how to find the value of the combined V and D model. Sometimes they'll ask you to find out the parameters in constant E model. First, write the value in terms of combined V and D model, and then substitute beta is equal to alpha, then you'll get the value here. Okay, substitute the values, same 14 product. Okay, 14 parameters. Similarly, constant E model also. Okay. Next, you can go for the next most important topic, that is some discussion on limitations of scaling. So here we are having different scaling limitations on effect here, because whenever we are going to scale down the transistor, so at the same time there are some parameters, there are some important effect will be exist in the some problems also. They causes some problem in this case. So that what are the problems and how to prevent all these things we can discuss now here. Okay. So first one in this case is the limitations of the scaling is substrate doping. Okay. In the substrate doping, again we are having substrate doping, that is the substrate doping scaling factors, and also we're having depression with scaling factors here. So depression with, and these two are the main important in case of substrate doping. Similarly, second one of the limitation is limits on the miniaturization. Okay. So these are the topics we can discuss now. Okay, let's go for substrate doping, the main important thing in this case. So that is, just observe here the substrate doping. So what happened now? What happened with doping? That means the doping is increases, what happened? Doping is decreases, what happened? So we know that in the mass structures, so we're having, so up to now, we're not discussed about some effects. Okay, various effects we are not going to declare. We are going to assume those effects will be neglected. Okay, that means the example for that one is built-in potential. Okay, in the circuit, we are having a built-in potential. So the built-in potential is represented by VB. So this VB depends upon the substrate doping level. Okay, the built-in potential, for example, let us go for PN junction, for example. In the PN junction, when the junction is formed, so at room temperature, so there is some voltage be exists. That voltage you can call it the built-in potential, or we can consider it the cut-in voltage. Isn't it? For silicon, it is 0.6 volts, and germanium it is 0.3 volts. Right? This is called built-in potential. Okay. So the same way in MOSFETs also there exists a built-in potential, because we are using the semiconductor devices there, semiconductor layers. So whenever the junction is formed, there must be some built-in potential be exist depending upon the doping concentrations here. So here the main important thing in this case is the substrate doping. Okay, the substrate doping. That means the built-in potential depends on substrate doping level. Okay, built-in potential depends on the substrate doping level. That is, so up to now we are not considered this built-in potential because we are having the value of VDD which is higher than more than the value of the built-in potential. So we neglected that value. Okay, we neglected the value in the for up to now. Okay, but during the scale down features, what happened during the scale down features? So what happened? The value of BB will be increases, and during the scale down, we are going to scale down the VDD level also. Okay, we are going to reduce the value of VDD. So therefore, so in that particular case, we're not going to neglect the value of VB because we are going to scale down the value of VDD. For example, if the VDD is equal to 5 volts, okay, the value of built-in potential is approximately 500 millivolts will get. That is 0.6 or 0.5 or 0.6 volts, right? In case of silicon, because in the VLSI we are not going to use the germanium material, we are going to use only silicon material. So cutting voltage, that is the built-in potential is around 0.6 or 0.5. Okay, so that means when high is that the maximum voltage VDD 5 volts is applied. So built-in potential we are going to consider in this case is approximately 500 millivolts. Okay, this is the built-in potential. For example, if you scale down the value of VDD, so because in this case, when the VDD is very high, 5 volts, VB is got 500 millivolts, that is 0.6 volt, 0.5 or 0.6 volts. So this is the VDD is a very higher value compared to the value of VB. So therefore, we neglected the value VB from our discussion. But during the scale down feature, that means as the technology goes on increases, so we are going to reduce the size of the transistor. At the same time, we are going to reduce the number of parameters by using scale, can be scaled down, just we are discussed now there. So here the VDD is also we are going to scale down. That is already we discussed the 1 by alpha times 1 by beta times, right? So therefore the VDD will be scaled down. So the value will be not close to value of 5 was now there. Depending upon the size and technology, the value of VDD also changes, so decreases. So as the now in this case, what happens is the value of VDD, there is no chance. Okay, sometimes the VB is higher than the value of VDD, and the value of VDD is very nearer to the value of VB. So in that particular case, so what happens? We are not going to neglect. That means, for example, when 1.5 volts, when VDD is equal to 1.5, in some technology we are going to use VDD is equal to 1.5 volts. So in that 1.5 volts, the VB is approximately 0.6 or 0.7. Okay, so in that voltage cannot be neglected now because 1.5 and 0.7 is very nearer. So that in that case, we are not going to neglect the value of VB. So we have to include the value of VB also. So that is the main important thing to remember. Okay, so now, so similarly, the substrate doping also, that is in the fabrication of the transistors, the substrate doping also plays a very important role in the transistors fabrication, right? So that is also very important. So let us consider the substrate doping scaling factor. Okay, so let us consider the substrate doping scaling factor. So in order to reduce the channel length of the transistor, because we are going to reduce the transistor, that means as the technology goes on increases, the channel length is decreases. Okay, length of the channel will be reduces because we are going to represent the length of the transistor will be to indicate the size of the transistor. Length is very important. So what happens is to scale down feature. In the scale down features, we are going to reduce the length of the MOS transistor. So whenever we are going to reduce the length of the MOS transistor. So what happened? Our aim is we have to scale down the depletion region because the channel in the MOS structures there is we are having 2 different layers which join together. There exists a PN depletion mode between the 2 different materials. Okay, so therefore what happened? Depletion region width also we have to remember. We have to take care on this case. That means whenever the channel length is reduced, the depletion region width also we have to scale down. Okay, so it is very important. Otherwise, what happens is in the source region, some depression region will be exist. The drain region also some depression region will be exist. So what happens if you are not scaled down those depression region, so there is a chance of meeting those depression regions of source and drain. So to eliminate that one, we have to reduce the depression region also. Okay. So therefore, depression region, and remember the equation already I discussed in the previous class. So one formula I given, the width of the space charge region is inversely proportional to the concentration, right? Width of the space charge region is inversely proportional to concentration, right? So there is the, so we have discussed W width is equals to 1 by capital N. Already we discussed here. That means width of the space charge region is, we are assuming W there. Okay. In this case, this is the concentration. So when the concentration is doping concentration is very high, width is very low. When the doping concentration is very low, width is very high. So here we are assuming instead of W, we are assuming D. The width of the space charge region is, we are assuming D. Okay. So therefore, here the proportional. Remember, we got this formula from this equation. From this equation. Remember, this equation is very important. Okay. So width is the space charge region. Okay, space charge region for the junction, depression region of the junction is given by square root of. Okay, already we can derive this equation in the step graded junction of the PN junction. Okay, so there's two epsilon SI, there is silicon permittivity and absolute permittivity into V divided by Q into NB. Okay, that means we can say that D is proportional to, we neglect, no, we all these things here, 1 by doping concentration. Okay, D is proportional to 1 by doping concentration. So there is D is inverse proportional to 1 by, there are inversely proportional to doping concentration. Now here the doping concentration, because we are going to consider the substrate doping, so we are going to consider here this equation, right? So therefore, just remember now here D is equals to so here we're going to consider here D is equals to square root of 2 epsilon SI, that is the permittivity of the silicon material, and absolute permittivity into V. V is the applied voltage, we will discuss now, divided by Q and NB, where NB is the doping concentration of the bulk material, bulk concentration. The bulk is also known as substrate, right? So therefore, where, just remember, where epsilon SI means is the relative permittivity of the silicon. Relative permittivity of the silicon, it is approximately 12, okay, 11.7 or 11.8 approximately. So that value can be approximated to 12. And what is the relative permittivity of the silicon dioxide? It is approximately 4. Don't confuse in this case. Okay. Epsilon SI is the relative permittivity of epsilon suffix SI. So SI is the silicon. Silicon permittivity is approximately 12, and silicon dioxide SiO2, Si, okay, O2, that is the insulating material we are using in the mass structure SiO2. So epsilon INS is nothing but relative permittivity of the silicon dioxide layer, that is approximately 3, actually it is 3.7 to 3.9. So it can be approximately to 4. But here we are using only epsilon Si. So relative permittivity of the silicon material, it is 12. And epsilon naught is the absolute permittivity of the free space. Already we discussed. So it is 8.854 into 10 power of minus 12 farads per meter. And this is given in terms of centimeters. It is 8.854 into 10 power of minus 14 farads per centimeters. And where V is the effective voltage across the junction. V is the effective voltage across the junction is given by applied voltage plus built-in potential is the applied effective voltage. Okay, number V is equal to applied voltage plus VB. where VA is the nothing but because the applied voltage there is a VDD plus VB also you have to consider. Okay, so there is the V is the applied voltage plus built-in potential, and Q is the charge of the electron. Q is the charge of the electron, and NB the doping concentration of the substrate material. Okay, doping level of substrate material. Next, VA is the maximum value of voltage. There is a maximum voltage you can apply, applied voltage, VDD, we are going to apply here. And VB is known as the built-in potential. Already we know that built-in potential of the junction. Okay. Okay, what is the built-in potential? Basically, it depends upon KT by Q. So this formula, KT by Q, natural logarithm of 4. In case of PN junction, we are in two P material and N materials. So that's why we have considered Na Nd by Ni square. But here we are using the substrate doping level. So Nb we can consider the bulk material. And if you consider that N channel if it is, it becomes Nd. And this is a Na. Na means accepted. Substrate is a P-type material. So Nb, okay. So Nb Nd by if it is a P-type transistor, then it becomes this becomes Nb and this becomes Na. Okay, there is a difference. Okay, Vb built-in potential is equal to KT by Q, right? Natural logarithm of Nb Nd by Ni square, where K is the Boltzmann's constant, T is the temperature, Q is the charge of electron, and Nb the doping concentration of the bulk material, that is substrate material, and doping concentration of the donor N-type material, and this is the donor level. Okay, now this is the intrinsic concentration. Okay, so there is the Nd means the source and drain doping concentrations, and Na is the intrinsic concentration of the silicon. So in case of 5 micrometer technology, already we discussed there. On 5 micrometer technology, the built-in potential is equal to 500 millivolts. That is, when Vd is equal to 5 volts, we are having Vb is equal to 500 millivolts, approximately 600 millivolts. And here Vb is neglected for scaling consideration because we are having the VDD is a higher value compared to the value of 500 millivolts. So under this condition, we can replace Vb, that is the depression, that is this equation. Switch charge width is equals to 2 exponent SI exponent naught. V can be replaced by VDD because this is VA plus VB. VA is equal to VDD plus VB. VB can be neglected, so we are having VDD here divided by Q into, and what type of bulk material? Q into Nb. Okay, this is the formula, right? Depending upon that, we can scale down the value now. So VDD is scaled down by 1 by alpha, and D can be this is the depressing width. Okay, depressing width means substituting the formula here. Okay, we are going to substitute the formula in this case. So you will get the value D is equal to calculating the value in this case. Okay, so another thing in this case is NB also, the doping concentration. So NB also we are going to reduce. Means, as you remember, as the VD decreases, because we are going to scale down the value. So what happened now in this case? So we are going to increase the doping concentration. When you increase the bulk doping concentration, so what happens? The spectra region is decreases. So as the spectra region is decreases, so automatically what happens? The field is increases there inside the spectra region. So voltage VB will be increases. Okay, so remember that point here. When the doping concentration is increases, okay, as we know that the width of the spectra region is decreases, but what happened? VB is increases because from the figure, the equation, from this equation, just remember, from this built-in potential equation, VB is proportional to the doping concentration of the bulk material. Okay, so therefore, and remember, as the doping concentration of the bulk material increases, so what happened? From this equation, the doping concentration NB increases, the depressive width is decreases, right? So as the depressive width is decreases, okay, remember, okay, so depression reason is decreases. Why this decreases? Because NB increases. As NB increases, automatically you can say the VB will decreases. Okay. So therefore, so here we are having the conditions there. As NB is increases to reduce the value of D, so that VB is also enlarged. That means it is typical values here. NB is equal to number of 5 cubic centimeter per volume, and ND is equal to number of 20 per volume. Then VB can be replaced by 0.88 volts. You'll get. Okay, that means as the doping concentrations are increases, okay, you will get this value. So therefore, at the same time, at the same time, what we are going to do now by increasing the doping concentration. So at the same time, we are going to reduce the voltage VDD. Okay, to reduce the voltage VDD. So that means we are going to scale down the value of VDD. So when this condition, when the VDD is scaled down, so and VB is increases because of increase the doping concentration. So what happened now? The previous condition, that is we are neglecting the value of VB in the previous, but now because of VDD decreases, so we are not going to neglect the value of VBB here. There is no longer they exist now. So that means the value of VDD is no longer compared with the VB. That means the VB is also this there. So you have to take the value of VB into account for scaling. Okay, in the scaling process. So therefore, depending upon the scaling factor, we are going to formula substituting here VA is the actual voltage is equal to M times the value of VBB. When M taking any value, substituting V is equal to V is equal to VA plus VB, that is MVB into VB. Depending upon that, VA can be scaled down by beta, VS is equal to M, that is scaled down voltage is equal to MVBB by VB by beta plus VB. So depending upon that, we are going to represent the scaling factor is equal to beta plus 1, beta plus M into beta into M plus 1. Okay. So the like this. Similarly, VS, where VS is the effective scale voltage across the depletion region. Similarly, the bulk concentration also we have to scale down here. Okay, depending upon the when the voltage decreases, scale down. So definitely we have to change the value of NB also. NB can be replaced by alpha square into beta plus M by M plus 1. Okay, and D is scaled down by 1 by alpha. So these are things you have to remember in this case. Okay. Right. So this is the effect of a scaling factor on the substrate doping level. Okay, remember all these values in this case. In the next class, you can go for the depressive width, the effect of the scaling factor on the depressive width. Okay, already we discussed depressive width. And as the doping increases, what happened? We will reduce the depressive width here. So depending upon that, we can consider it now here. Okay. So that is today's class. We will discuss in the next class. My remaining topic. Okay.